Starting. Good afternoon, everyone. At least good afternoon in the UK, where Max and I are. I know we have people from all over the world today. My name is Hector Beade. I'm the design director at Night Architects, and I'm here representing the IABSE British group. Welcome to this webinar. Thank you very much for joining live. I'm sure you will not regret it. I expect the presentation to be excellent. No pressure, Max. I'll briefly introduce IABSE first as the organizer of this session. IABSE is the International Association for Bridge and Structural Engineering. It was founded in 1929, it's close to being 100 years old, and it is a forum to collaborate, exchange knowledge, and disseminate it to contribute to the progress of structural engineering in any of its aspects and the awareness of our responsibility to society. IABSE has members in more than 100 countries, and it has more than 60 national groups. If you want to become a member of IABSE, which I would encourage you to do if you're not already, it is likely that there will be a national group close to where you're based. The organization fosters education and cooperation, and as part of these goals, it hosts technical groups on different topics. Some of them may be aligned to your expertise and interests, and you could consider joining them. You can find more information about that on the website. And it also publishes the reference journal Structural Engineering International, SAE, publishes technical books and conference proceedings. Linked to this last point, there are several really interesting and highly recommendable symposiums, congresses, and other events organized by IABSE every year. I'll share some of the upcoming ones. There will be a symposium in Tokyo, in Japan, in May. The topic is environmentally friendly technologies and structures, focusing on sustainable approaches. I'm sure it will be a fantastic event, and early bird registration for that symposium is open at the moment. You can find more information on the IABSE website. Slightly later in the year, the IABSE Congress will take place in Ghent, in Belgium, in August. The topic is the essence of structural engineering for society. In April 2026, there will be another symposium in Copenhagen, in Denmark, about bridging advances, technologies, structural innovation. You're on time not only to attend to this one, but also to contribute as a presenter, as the abstract submission period is open at the moment, up to the end of March. IABSE organizes a series of awards, People, Paper, and Projects and Technology Awards. I'm pleased to be part of the jury of these last ones, the Project and Technology Awards. You can submit your entries for these awards up to the 31st of March as well. The event, the gala dinner where the winners will be unveiled, will take place in November in Zurich, and anyone is allowed to register for that event as well. Moving to the UK, to the IABSE British group, there will be a conference in April in Leeds, in England, the Future of Design conference that takes place twice a year in the UK, and it is fundamentally for early career designers from an engineering or architecture background, but everyone can attend, and it's always high quality. The British group, I'm gonna stop sharing. The British group also organizes their own awards. One is the Mile Medal, awarded to structural engineers who have excelled in structural design in their careers. And the other one is the Nethercore Prize, which is awarded to early career architects, engineers, and designers for a paper on a project, but focusing on excellence in communication, in conveying ideas, and in storytelling. Max Clayton, who's here with me, has been the winner of this year's Nethercore Prize. I was part of the jury of this one as well, and I can tell that the paper not only included a very well-communicated process, but also presented an extremely exciting project. I will probably introduce himself in a second. Just want to say before that this presentation is being recorded. It will be uploaded to the e-learning section of the iabse.org website, together with previous webinars and other excellent information that will allow you to learn about different aspects of our work from other excellent professionals. So moving to the presentation, Max is an engineer and associate at the firm Structure Workshop. he will talk a bit more about what they do in his presentation. And the fantastic paper that allowed Max to win this year's Navigal Prize is called Fern the Diplodocus, Structural Tale. Please participate in the webinar and ask questions as they come to your mind by writing them in the Q&A section you will find on screen. I will read them at the end for Max to answer. And the stage is yours, Max. I'm looking forward to hearing about a freestanding post-tension bronze dinosaur skeleton. So over to you.
Yeah, thank you, Hector. Can you see that all right?
Yeah, perfect.
Yeah, well, I'm really pleased to be here talking about this project. Like Hector said, Fern the Diplodocus. Not a typical structural engineering project, I'd say, but one of the most interesting I've ever worked on. Sorry, that's just my doorbell going on in the background. So yeah, today I'm going to tell you about Fern the Diplodocus, who you can see on the screen here. And it was an absolute privilege to design this new project for the Natural History Museum in London. Aside from being a brilliant museum itself and research centre, it's an incredible, wonderful building. It's a Victorian masterpiece designed by Alfred Waterhouse in 1881. And as you can see here, it is a slightly mad but marvelous structure. And it's embellished with terracotta animals, both living and extinct. It was originally envisaged as a cathedral to nature, and I think that it really, really is. And it's probably my favorite building. And I particularly love the playful details like these terracotta monkeys who you can see climbing up the walls. Now, recently, the museum's gardens have been transformed into a biodiverse green space. This is the Urban Nature Project, and that's what you can see here. And the gardens tell the story of life on Earth from the very beginning to today. And you enter the site from an underground tunnel coming from the underground. And as you emerge, you're surrounded by ancient rocks and plants from different eras in Earth's history. So it starts over 3 billion years ago at the dawn of life. And every step forward you take through the gardens takes you forward 5 million years in time. And there's a new dinosaur called Fern situated in the Jurassic period. The design and production of Fern was a set piece within this wider scheme, and it went out as a competition in 2020. And it's an exciting project at the intersection of structural engineering, paleobiology, advanced digital technology, and ancient forms of craftsmanship. And that's the story I'm going to tell today. First, I'll tell you about the team behind Fern and how we became involved in it. So I work at a company, like Hector said, called Structure Workshop. And we're a relatively small engineering practice based in South London in this lovely Victorian muse that you can see here. And our founder, Pete, set up Structure Workshop 20 years ago. He's been my mentor for about 10 years. And together and with the team, we've designed some interesting and some quite unusual structures. We work at a range of scales and building types, often with a focus on innovative material use and low carbon design. We particularly enjoy working for cultural institutions and public buildings. So this is Homerton College Dining Hall in Cambridge that we did recently with Field and Fowles Architects. But a third of our work is in the arts, and it tends to be some of our most interesting and unusual work. And it's often quite large, whether it's in a gallery space, like this one you see here with the artist Conrad Shawcross, or outside in a public setting. We have quite a lot of experience designing public sculptures. And this specialty has put us into close contact with a huge range of really, really interesting artists, studios, and fabricators. One such company is called Factum, who led the team behind Fern. And this is their workshop in Madrid. It's quite an amazing place if you ever visit. Factum produce works for contemporary artists. And they have an extremely innovative approach to fabrication, merging the most advanced forms of digital technology with traditional craft skills. And when you visit their workshop, you're blown away by the incredible objects that they're making. So this big thing you see here is called the Colossus of Constantine, and it's a full-scale recreation of an ancient Roman statue, which we provided the engineering input for. And the amazing thing about their workshop is just the number of seemingly priceless artifacts that they have scattered around. So behind the statue, you can actually see a replica of Da Vinci's The Last Supper just casually hung up on the wall. We first met Factum when we collaborated on a series of bronze sculptures for the artist Conrad Shawcross, the largest of which has just been installed in central London as part of the Crossrail project. With our experience designing large public sculptures and Factum's expertise in advanced fabrication methods, we felt we were a great match to take on this project. This project being a competition for a brand new bronze dinosaur. And it was going to be based on, but distinct from, the Natural History Museum's famous Dippy. And you might have heard of Dippy. This is it. It's been called the most famous dinosaur in the world, and it stood in the grand central hall of the museum for nearly 40 years. Dippy, that you can see here, is 120 years old, and you might think that's quite young for a dinosaur. But the real dinosaur was the Diplodocus, which lived in the late Jurassic period, 150 million years ago. And that means it was already an ancient fossil when T-Rex and Triceratops were roaming the world. In fact, one of my favorite facts is that the T-Rex is actually closer to us in time than it is to the Diplodocus. Anyway, millions of years later, in 1898, railway engineers working out west, the USA in Wyoming, uncovered this gigantic thigh bone. And word spread quickly. And it was at this point that the Scottish-born American industrialist Andrew Carnegie got wind of the discovery. He was one of the richest men in the world, in fact, one of the richest people ever. And he'd just set up a new museum in Pittsburgh. And he decided that this colossal animal would be the perfect centerpiece for the museum. So he set about buying it, and he funded the rest of the dig. When scientists formally described the specimen in Pittsburgh, they named it Diplodocus carnegie after him. And these absolutely beautiful drawings were produced as part of the original scientific paper describing the specimen. The story goes that King Edward VII saw this drawing when he visited Carnegie in his Scottish castle. And he basically suggested that the Natural History Museum in London ought to have a specimen just like this. Mr. Carnegie took this to heart and he had an accurate cast made of the original fossils. This was a huge, huge undertaking. Expert Italian model makers were brought in from Florence to mold and cast precise replicas of the bones in plaster of Paris. And it's this replica that was sent to London. And this photo shows the grand unveiling of Dippy in 1905 in the reptile gallery of that museum. Over the coming years, other replicas of Dippy were sent to cities around the world, including Berlin, Paris, Buenos Aires, and others. And some of you have probably seen them in your local museums. But the Dippy in London has been on display almost continuously since then, and it took center stage in the main hall from 1979 and it's been seen by millions and millions every year. In 2016, Dippy left the museum and went on tour around the UK. This is a picture of Dippy in Norwich Cathedral, and I went to see Dippy here, and it was a really amazing setting, you know, an amazing building for the amazing creature. So now Dippy's been replaced in the museum by a magnificent blue whale skeleton called Hope. But that is not the end of the story for the Dippy specimen. There is a new chapter, and that's Fern. The brief from the museum was for a new life-sized bronze dinosaur based on Dippy to be exhibited outside permanently. It must look as lifelike as possible with minimal visible structure and, most importantly, without the appearance of being propped up. So when the museum asked us, is it possible? We all agreed. The only answer was absolutely. Because what an amazing project to be involved in. We just had to figure out how we were going to do it. And it is a unique structural challenge. And nothing like this has ever been done before. So just to reiterate, the new dinosaur was to be life-size. So that's 25 meters long, made up of over 292 bones. And bronze is heavy, and it had to go outside in all weather for 100 years. not protected in a gallery. And unlike a gallery specimen, it had to be designed to be climbed on. We had visions of drunk tourists and stag doos hanging off the neck. And the structure had to be largely invisible, and most importantly, without any props under the long neck or tail, which is how these specimens have always been supported. So we had our mission, but could it be done? At this point, we genuinely didn't know. Before showing you what we came up with, I'm going to tell you a little bit about the engineering marvel that is the real animal. This is its skeleton, and the most striking aspect is obviously the huge size. It's one of the longest animals to have ever lived, and that long neck and tail needs supporting. What we find is that it's an incredibly elegant and efficient natural structure. Those long neck and tail are cantilevers, and they're held aloft by thick, strong ligaments running along the spine and anchored back to the hip, and that's what you can see there in red. And they would have been under great tension and allowed the Diplodocus to hold its neck and tail up without effort. And with tension comes compression, and the vertebrae of the spine have to resist huge compressive forces without adding too much weight. And so they're hollow, like a bird's, for maximum strength to weight ratio. And then at the center, all these forces are balanced at the hip, and the great dinosaur's weight is held up mainly by those back legs. That green X you can see there marks roughly where the animal's weight is centered. And because it's near the hip, the pivot point, the animal could have actually reared up on its hind legs. I don't know if anyone's a fan of Jurassic Park here, but this image of the Brachiosaurus could have actually happened in real life. Taking a closer look at those vertebrae, we can see how efficient they are. So on the left here is a 3D printed structural node that Arup did a few years back. It's been optimized by a computer program to minimize its weight while maintaining strength. On the right is one of the cervical vertebrae of the Diplodocus, so one of its neck bones. And I just think the visual similarities are really interesting because the vertebrae has also been optimized and refined, but rather than using a computer, just by millions and millions of years of natural selection. The real animal is so elegant, it's no surprise that a lot of our solutions ended up being inspired by nature. And here is the final design. So everything in grey is the natural biology of the dinosaur cast in bronze. And the colourful parts are the engineering additions we've made. And if they're quite hard to spot, that means we did our job well. So it's a 6-ton skeleton cast entirely in aluminium bronze. The length of 3 London buses and the tail alone is a 15-meter cantilever. And as you can see, no props under those cantilevers. So if I take a cut through the center of the dinosaur, we can see inside and we can see the engineering a little bit more clearly. The bones themselves form the main structural elements. Each one is a separate hollow casting, and the entire structure has almost no welding. Those vertebrae, separate vertebrae, are held together with small steel structural bars. We call them tendons. There's a lower tendon inside the vertebrae and an upper tendon at high level. Now, these tendons have been pre-stressed, they've been pulled tight, and they pull those vertebrae together and hold them in compression to form the main structural spine. And then just like the real animal, those tendons are anchored back to the hip bone or the ilium. Those two cantilevers largely balance each other out, and most of the weight is held up by the strong back legs. In summary, this is how it works. So you might think our job is quite easy, just look at the dinosaur and copy it. But in the design process, we exhausted every other possibility before eventually converging on these natural solutions. Our first idea, the way we all really wanted to make it, was just incorporate a thick steel structural bar hidden inside the bones. Factum have done this before. They've made some amazing bronze trees, which you can see here. And for us, it'd be quite easy to make, relatively easy to design, and we'd know what we were doing, and we wouldn't have to worry about the bronze at all. But we soon realized this was impossible. This image will show you why. So these are cross sections of one of the neck vertebrae, as if we'd taken a CT scan. And we found that the bones are just too variable in shape to fit a big steel beam on the inside. But there's quite a lot of material there to work with, as you can see. So we sort of realized that we had to use the bronze itself as the structure. Our next idea was to just weld it all together and for the bronze itself to form the structure. We've done this before with various sculptures, like you can see in the background. But there was a problem with this approach too, because unlike this sculpture you can see here, well, welding this would be an absolute nightmare. Not only would the welding be incredibly difficult, more importantly, it would be almost impossible to properly inspect those welds, and they'd be all mostly critical. So the failure of one weld could just cause the neck to fall off. As engineers, we want to be able to sleep at night. And it would have been a shame to cast these beautiful bones in fine detail and then weld across them, covering it in scars. And that's when we realized we needed a way to connect the individual vertebrae without welding. And we decided to do this by pre-stressing them with tensioned steel bars. I'm going to briefly explain how this pre-stressing works. There's usually something that's done with concrete. If you have a beam and you attach it to a wall and you apply force to it, it will bend. So the top will get longer, go into compression, and the bottom will go into, so the top will go into tension, the bottom will get shorter, it will go into compression. That's fine for a solid beam. But if your beam or your dinosaur neck was made of separate pieces, you cannot get tension, it will just fall apart. But you could put a bar inside and stretch that bar. And as it tries to contract, it pulls those pieces together and they become compressed. And the basic idea is that this compression can overcome the tension from the bending. They cancel out and the pieces are held together and they act like a solid beam. It's actually more effective if you put the bar near the top in the zone where the tension wants to form. You can actually increase this effect by moving the bar even higher. And it's a bit like a lever. The further the bar is from the center of the beam, the more efficient it is. It actually creates a reverse bending in the beam, like you can see here. And this reverse or negative bending can be calibrated to match the bending from any force applied to the beam. So when you combine the effects of pre-stress and the effect of gravity, you can make them cancel out and you get a happy dinosaur. That is the essence of our structural solution. And it sounds sort of simple now in hindsight, but it took us ages to conceptualize and get our head around. There's a lot of head scratching, a lot of late night conversations, and a lot of sketching to figure out the design. And there was also quite a long way to go from conceptualizing the solution, like you can see here, to actually completing the design in detail. I'm going to talk about the detail now. One major issue was, how do you take a totally biological form and apply some engineering logic to it? So these are the vertebrae themselves, which are the main structural components. And first, a team of scientists at the museum digitally scanned every one of the 292 bones in extreme precision in 3 dimensions. Factum then assembled these bones virtually with input from the paleontologists and us, the structural engineers, to create a new pose for Fern that was biologically accurate, buildable, and structurally sound. Factum then sent us low-resolution versions of these bones, because as engineers, we don't really need the fine surface detail, just the basic shape. Then we modified the bones, so we applied some geometric logic to them that we could define and design. So like you can see here, what we did, we flattened the end of the bones to create elliptical bearing faces, which match exactly to the adjacent face on the next bone and give you a good contact area. But the bones are hollow, so we also had to model the void inside the bones. We added detail there too. So that's what this blue shape is. It's sort of the hollow void. And when you subtract this blue shape from the external shape, you get a hollow vertebrae with an inside and an outside surface modified with our engineering components. And then we need to analyze it. So we perform a computerized simulation to predict the forces, stresses, and deflections. So any fans of FE will know what this is. This is an analysis mesh, which we use in our finite element software. and then we can analyze it. And what you see here is the result of that analysis. This is showing the stress in the bronze, and basically the hotter the color, the greater the stress. And this is how we check that the vertebrae won't crush or be overstressed. And that's just one bone. We actually did this for the whole dinosaur. So along the pre-stressed spine, that's 50 unique vertebrae and nearly 300 bones in all. We used this model, this global model, to predict the behavior of every single structural element that went into our structural design. For a while, we weren't even sure we could get the model to work. And once it did work, it took 2 days to run on my laptop every time we wanted to change something. One thing that our early analysis revealed was that the vertebrae failed in the most extreme design situations. The bronze just wasn't strong enough. I was as stressed as those vertebrae for a while. But we did find a solution. We incorporated internal strengthening fins inside the hollow bones, which you can see on the left. Nature actually had a similar solution. So on the right, you can see a real CT scan of a genuine fossil neck vertebrae. See, dinosaur bones are hollow with internal structure. They're actually pneumatic, which means they're filled with air. This maximizes the bone's strength and stiffness while keeping its weight to a minimum, which is absolutely crucial for these long cantilevers. Now, birds, being the descendants of dinosaurs, have this adaptation too, which is what allows them to fly. And this solution was only possible thanks to the team at Factum, who devised a really clever way of fabricating these internal features on the inside of the bronze castings. Another problem we encountered was that, as you can see here, the neck vertebrae become smaller and more delicate as you get closer to the head. This makes sense because the forces and the bending is greatest at the base. But to overcome this bending, the pre-stress at the base has to be quite high. But that high pre-stress would have ended up crushing the more delicate bones towards the end. And the breakthrough in our thinking came when we realized that we could use multiple bars, which get smaller and they step down in size as you go along the neck or tail. And instead of applying our pre-stress in one big lot at the end, we add the tension to each bar in sequence as you build the neck. And that tension gets smaller as you go from one bar to the next. Now, in our case, the upper tendon does most of the work against gravity, and the lower tendon has a smaller pre-stress and deals mainly with lateral loads. So you can imagine the position of that upper tendon is really important, like we talked about earlier. The higher you make it, the more effective it is. And so there's a lot of debate in our office as to where best to place it. But when you study the anatomy of the dinosaur, you do find an ideal location. So as you can see here in this original drawing, the vertebrae are connected by their main joints towards the bottom. But at the top, the dinosaur has these pointy bits called spines and processes. And this is where the ligaments and muscles would have attached in life. As we run our upper tendon between these spiny structures, as they sit in almost the same place as those of the real dinosaur, and they're hidden from view. Now, as we saw earlier, by having them at high level, you can put negative bending into the structure. And so this clip I'm about to show you shows what happens when you vary the tension in that upper tendon. See, by adjusting the pre-stress, we can effectively reverse the effect of gravity and lift the head up. And what that does is it reduces the peak stresses in the bones, and it means there's almost no net deflection. See, we thought that was quite a clever solution, and I think Fern is nodding along in agreement. This is a close-up of that pre-stressing assembly. It's the only part of the entire design that isn't bronze. So the tendons themselves are possibly the most critical part of the entire design. They were produced by a British company called McAloy, based near Sheffield. And our design was only viable because McAloy gave us the confidence early on that they could produce what we needed technically, and they're unusual pieces of design. Now, although they produced these bars as a product, everything we had fabricated was smaller, unique, and completely bespoke. And they're quite simple. Some people assume we used some kind of steel cable, but they're actually solid bars made of high-strength stainless steel. They stretch less than cables, and they're 3 times as strong as normal structural steel. And Macaulay actually manufactured them with a curve to follow the shape of the dinosaur's spine. And the ends are threaded, like you can see here, and I've highlighted in blue the nuts. And those nuts screw onto the threaded ends, just like they would if it was a bolt. And by tightening that nut, you stretch the bar, and that's how the tension is applied. These in blue here are the couplers, and they have threaded holes coming from each direction. And that allows you to connect one bar to the next, and it allows you to step down the size of the bar as you go along the neck. And we also incorporated steel barrels around the upper tendon, and they stop the pre-stress in the tendons from folding up the spine when you first tension them. But once the creature is fully assembled and the bones weigh it down, gravity and pre-stress are in harmony, and there's no force in those barrels at all. Those tendons go all the way back to the hip, or the ilium, which they anchor into, just like the real dinosaur. And this is a really critical zone, right at the center of all the forces. And its size, the size of this bone, allows us to access the inside. And that's what we call the stressing chamber. The top spine actually comes off like a lid. You can get inside to add tension to the nuts on the tendons. So those things inside there, you can see those are the hydraulic jacks, and we use them to apply the tension. And right in the middle is an element cut from solid bronze, which connects the front and rear tendons and balances the forces. This is a picture I took of Dippy in Norwich Cathedral. And what we're doing, we're looking up from underneath. We're looking at the dinosaur's back, and you can see the ribs of the dinosaur and the ribs of the vaults behind. We noticed the bones are quite gappy, and we needed to fill that space for our pre-stressed structure to work, to transfer compression along the spine. So we devised a kind of bronze cartilage infill to transfer compressive forces and to fill that gap. The joints you can see here, you can tell they allow articulation and movement, but we obviously had to prevent any movement. So our cartilage were flat surfaces. And this is a cut through the tail, and you can see the cartilage plates here in yellow. The bones themselves have loose fit holes to the tendons to allow you to assemble it, and the cartilage has tight fit holes. So they touch the tendon, and they have studs pointing forwards and backwards into the vertebrae, which transfers shear and torsion from one bone to the next. So everything is locked in place, and the bones can't slide or twist against each other. At one end of the pre-stressed spine, we've got the head. And then the other, we call this the tail whip. And it's an amazing piece of anatomy. That's 6 meters of tail in that photo. And the really thin part is actually 3 meters long. And it's the size of your index finger. There was a lot of discussion in the office as to the best way to make this piece. There are loads of suggestions. For example, do we make it out of something really light, like fiberglass or carbon fiber, and paint it? But in the end, we found that solid bronze was the way to go, and our analysis proved that it works. Although having said that, it is the most delicate part of the dinosaur. If you were to try and hang off it, and I would just like to be really clear, it's not advisable. But if you did, the tail would break. But at a predefined point where we've designed in a shear pin that can break predictably and more easily be replaced, a bit like a lizard. Compared to all that, the legs are actually quite simple. And I think this image is a great summary of how those legs work. Partly because as engineers, it's great to see your drawings actually being printed out and used. So this is the workshop in Madrid where Fern was produced, with our design printed full-scale, life-size, 1-to-1. What you can see there is a solid bronze bar runs through the inside of the leg bones, the blue bit. So the bars are really strong, but by themselves, they'd be far too flexible. And so they're welded to the bronze cast bones, which provide the additional stiffness so that Fern doesn't shake or dance on a windy day. Now that man standing to the left there smoking a cigarette is Alvaro, who runs the foundry Fadamesa, who cast all the bronze bones and whose skills and experience were absolutely crucial. He would often tell us in the earliest meetings what he thought the thing should work, how he thought it should work, and how we should make it. And we did find he was often right. Key to the entire design was figuring out how to actually put this thing together. Once we understood this, a lot of the design followed. So it all starts at the ilium and the first two tendons, which are anchored into it. And you then add the dorsal vertebrae or the backbones, and you thread them on like beads on a string. And you do that until you have the creature's back formed, and you tighten the first two nuts, compress it all, and create a solid structural beam. Next, you mount this on the legs. And from here, you can screw on the next two tendons into the couplers and thread the neck bones. And you repeat this process, screwing on tendons, pre-stressing a set of vertebrae, until you've completed the neck and the body. Now, parallel to this, the tail is also being assembled in exactly the same way, piece by piece. And then these two objects, along with the head and the tail whip, will fit on a single lorry, and that's how they're delivered from Madrid to London. The idea was that on site, it would then be really easy to just bring the tail up, insert it into the ilium, tighten two nuts, and it's done. Obviously, life is not quite as easy as theory, but it did basically work that way. And that is our design. It's two cantilevers supported by steel tendons under great tension, anchored back to the hip and supported on thick pillar-like legs. Now, interestingly, Diplodocus is actually derived from the Greek. Diplodocus means double beam. Unfortunately, it's not a reference to our structure, and it is a description of some unusually shaped tailbones. But I do think it is a wonderful piece of serendipity. But then we had to create drawings so that Factum knew what to make. The reason I have all these images to show you today is because we ended up having to model every bone in 3 dimensions to fully describe the structural design. You know, every single bone was different. And to also make sure every piece actually fit together and that you could build the thing. When you compare our production drawing at the top to the original scientific illustration, you can see just how far paleontologists have come in their understanding of the animal. You know, far from being slow, droopy, and lizard-like, Diplodocus was upright, dynamic, and full of life. So we had our design, but there was immense trepidation at this point, because nothing like it had ever been done before. So a big question remained, could it actually be built and realized in the physical world? And I strongly believe if we didn't have Factum on our team, and if they couldn't make it, nobody else could have. Now, the production of Fern was really interesting. I'm going to tell you about that now. It was at the interface of the most advanced forms of digital technology and much more ancient artisanal processes. The Factum started with the high-resolution scan data, which you can see here, which had been virtually assembled into the final pose of the animal. Next, they applied our engineering design to those virtual bones. With over 50 pre-stressed vertebrae and 292 bones in total, you can imagine how involved that process was. And then we passed from the virtual world to the physical, and we found the physical world is far messier than the virtual world. And so the achievement in realizing the design can't be understated. And as you'll see, it's a very complex process, and it required the combined effort of dozens of dedicated and highly skilled craftspeople and technicians. The first step in the casting process was to 3D print the engineered bones, and you can see them here on the table. They're being prepared for the next phase, which is creating the molds. So those printed bones are first coated in a soft clay and then in a hard plaster to create a mold, which you can see here. That soft clay is then replaced by silicon, which sits inside the hard plaster and forms a negative mold of the bone. Next, wax is layered onto the silicon mold. The wax is that gruesome looking red stuff you can see here. And the woman inspecting the wax is Vula, who was responsible, among other things, for the digital files and applying our engineering to every bone. So she's probably one of the most important people in this whole process. And then you pop the wax out. And if you join those two halves, you have a wax positive replica of the original bone. The casting process used is called investment casting, and it's based on an ancient method called the lost wax process. The lost wax process is truly ancient. The oldest known examples of this technique are over 6,000 years old from the earliest civilizations of the Near East. At this stage, the wax is invested, which means it's coated in a heat-proof ceramic shell. This covers the wax both inside and outside, and it's protected in a clay cylinder, and that cylinder is what you can see here at the bottom. Now, when you heat it, that wax melts away, leaving sort of a negative space within the ceramic, a negative mold of the bone. And then the bronze, melted at over 1,000 degrees C, is poured into that mold to form the bone. And once the bronze has cooled and solidified, you need to break away that ceramic mold. And that's what you can see here. And what I love about this part is that it looks just like a fossil being slowly revealed from a prehistoric rock. And that's the process. And it is a little bit confusing, and it took me a long time to get my head around. But the full history of that bone is even more fun. So first, that bone was in a living dinosaur, and you can see that bone at the top left. Then it died, and it was buried, covered in sediment, and it formed a negative impression in that sediment. So that's the second image. And then over millions of years, minerals get in and they fill that space, and it creates a positive replica called a fossil. Only for that fossil to be dug up millions of later in America, and a negative mold was taken, followed by a plaster cast positive on the right, known as Dippy. Dippy was then scanned and 3D printed, and you can see a positive replica made on the bottom left. This 3D print was followed by a silicon negative, followed by a wax positive, followed by a ceramic negative, until finally today we get our bronze cast positive replica of the original bone. So it's simple, but the casting process is fraught with issues. So the wax itself can distort, especially in a hot Spanish summer. And as the cast bronze cools, it shrinks a little bit, and that can cause further problems like distortion and porosity in the metal. And it was really difficult to get right. And we were actually being exceptionally demanding of the fabrication with our engineering. Occasionally, we had to reject a casting. In the case of the vertebrae shown, the bearing face, which is that front face you see, where the bones meet, was just too thin to transfer the forces. And those bearing faces need to be perfectly flat, but the casting process leaves distortions. To solve this, the team at Factum came up with an ingenious solution. They actually rescanned every cast bone again in 3 dimensions, and they matched its position to the original digital design geometry. By doing this, they're able to tell exactly where the casting deviates from the design and by how much. And that's what you can see here. And they use this information to position the bone on a 6-axis CNC milling machine. And they use the virtual file to tell the machine exactly where to cut the bronze. The machine's tool mills the bronze surface. And by doing this, they're able to create a totally flat surface in the right position, which met the demands of the engineering. The final part is they actually then scanned every bone again and assembled the full dinosaur virtually so they could see how well it would match the original design and check it would all fit together. And so we're left with a big pile of disparate bronze bones. These are 8 of the caudal vertebrae here, or the tailbones. And it was time to start building it. And there are some great photos of this bit from the workshop in Madrid. So here, the technicians at Factum and Fadmesa are mounting the ilium on the legs to test its position. And then to construct the spine, we begin at the ilium and with the tendons protruding. And we start adding vertebrae one by one. And the largest vertebrae are nearly 100 kilograms, so it's not an easy task. That smiling chap in the middle is Jonty, who was in charge of the messy physical world of the assembly. Unfortunately for everyone, he basically bossed the whole process, solving problems as he went. And then once you have the torso of the beast ready, you mount it onto the legs, which you can see waiting for the spine in the background. And piece by piece, a dinosaur starts to emerge in the workshop. In this image, you can see where the tendon runs along the top of the vertebrae, concealed by the spines and processes. This is also one last opportunity to alter the position of various bones. The pictured here is Professor Paul Barrett of the Natural History Museum, who ensured that Fern is the most accurate Diplodocus on display anywhere. And the tail was also being assembled bone by bone. And once completed, it was installed. And this video shows that process. So this tail went on and off and on and off several times in the workshop as it was altered and adjusted. And this proved to be a really, really important rehearsal, because by the time the final installation in London, Factum had it nailed. Next, we hung 1/4 of a ton off the end of the neck and tail. Because despite all our calculations and analysis, design like this had never been done before, so we couldn't be 100% sure it would work as predicted until it had been physically tested. And this was a heart-in-mouth moment for everyone involved in the project. And when the load was released, it creaked, but it held, and I think you could have heard the sigh of relief all the way from London. This is Adam, who runs Factum, looking rather pleased that the tail held. Once assembled, it was really amazing. There was this huge beast lurking in the workshop. People would visit not really expecting it and just be blown away by this dinosaur. And it was really exciting to see the thing come to life in the workshop before the public unveiling. The final part of this story is the delivery and installation, and the challenges continued to the very end. Fern was delivered by land and by sea in a wafer deck truck from Madrid to London. And Fern only just fit, and they actually had to remove the tallest spine to get under the bridges. And it was originally covered, but they actually had to remove the fabric en route because it was flapping in the wind. And so I just like to imagine all the people driving on the motorway late one night, overtaken by a shiny bronze dinosaur. Fern was installed by the art handlers MTech. The intention was to crane Fern right over those tall trees you can see there in front of the museum. And it would have looked, I imagine, a little something like this. A brilliant photo from the 1980s when a Brontosaurus model was flown into Boston Museum of Science. Now, things didn't go quite to plan, but in the end, they did manage to reverse the lorry with an amazing bit of driving skill onto site. In the dead of night, Fern was lifted into place by 2 small cranes on the back of 2 trucks. It was a very stressful night, but we got it in. And things got simpler from here. The next night, the tail was installed, followed by the head. And after that, we have a dinosaur. And we are delighted with how it's turned out. As you can see, we did manage to do it without any props. And the result is that it really does feel more alive. You get a real appreciation for the living animal. Right at the start, the museum asked us, is it possible to create this dinosaur in bronze without any external supports? And with hindsight, I think the sensible answer would have been no, because it was really, really difficult. But there were a lot of talented and dedicated people collaborating on this project who realized the importance of the project and the opportunity it represented to do something amazing. Many of us will have visited the museum as children and will fondly remember being inspired by Dippy, like so many others have over the last 120 years. How often do you get to design a dinosaur? If you'd had told me as a kid that this would be my job growing up, I don't think I would have believed you. And across the project team, there was a level of dedication and commitment to the outcome that I don't think you'd get for any normal project. And it's all been worth it. I think it looks great, and we hope that Fern will continue to inspire people for the next 120 years. And all that's left really is to say thank you for listening to me. I'll let Hector take over, but I think we have time for a few questions. So thank you.
Thank you, Max. That was excellent. Thank you. Subscribe screen. Yeah. So, of course, yeah. Lovely presentation. So, I think evolution can be seen somehow as a design process, a slow and dramatic optioneering exercise. And vertebrates are very sophisticated structures, as you have excellently explained. So, excellent. It was a very charming idea, very ingenious design, and a very thorough and precise fabrication process. It has everything, and it has also one of the, well, probably the most beautiful structural analysis model I've ever seen.
That's high
Yeah.
praise, thank you.
We have a few questions. People, yeah, I'm thinking we have 4 questions. I'm gonna start with give time to people to think more questions by asking a couple I had. So yeah, it seems that you got a very unique brief, and you managed to get a team with all the skills. Probably not so many people will be able to do that, as you said before. How was the tender process? What was the how did you get involved in the project, and how did you get involved as a team? Was it you looking for the rest of the supply
Yeah.
chain, or
Yeah, well, Factum, who I think I introduced in there, run by Adam Lowe, are a really, really impressive company. Like they make all sorts of amazing things, and they led the team, and they sort of put the team together, assembled it, I suppose. So they came to us actually, having done a few sculptures with them in London in the past. You know, they make a lot of public sculpture, and that's how we first met them. And they do a lot of sort of preservation of cultural heritage, paintings, monuments, that kind of thing. So they assembled the team, and they really were best placed to sort of address it. And it went out as a competition, so we weren't the only ones going for it. I don't know who the other teams were, but there was a handful of teams, and we fortunately won. I think we said early on, yeah, of course we can do it. We didn't know how at the time, but we managed to make it work. So
that's how you get involved with the best projects, by not overthinking them sometimes. And was it the brief? So you talk about as the tail and the neck not being supported, a bit looking as light as possible. How specific was that in brief? Were you forced not to have any support,
there
or
was
you offered more than what it would
yeah.
be
I mean, the
expected?
brief was clear in that it just said as little visible structure as possible. And I think it said we don't want it to appear propped up. Now, it didn't say none, but we took it to mean, you know, we were trying to be ambitious, you know, and we felt if we had a prop under the neck and toe, which are those are the real challenges, we felt a prop would have been somewhat a failure on our part. And this wasn't like a sort of self-absorbed mission, you know. I really do think it makes the specimen more amazing sitting there in the gardens because of it. So, you know, we were worried there might be a time where we'd have to say, okay, no, sorry, it's not possible. But we tried really hard to make it work. It was sort of a mission in a way.
So, yeah, very good. I'm gonna go to the questions in the chat that people have here. Written a few more. So the first one is about well, you talked a bit about that, about how did you come to the decision of the post-tension solution, and what options did you consider? You mentioned that, but maybe you want to develop it further.
No, but there's more to talk about there. I mean, I could do a whole separate talk on the optioneering process because we considered absolutely everything. You know, from early brainstorms where like nothing was off the table. The fact was we didn't know how to do it at the start. So I put a couple of the main contenders in there, having a beam along the middle and welding it all up. It's basically because when I talk about the pre-tensioned approach and the idea of having tendons in tension and the similarities that have to the nature, like I said, it sounds almost obvious, but the reason we didn't go there straight away was because it was very difficult to make and very demanding of Factum. You know, it's definitely not the cheapest or easiest way of doing it, but in the end, we decided it was the only way of doing it. So we wanted something more straightforward. A steel armature concealed was obviously the preference. welding the whole thing was considered. We designed spigot connections between each bone, or we considered spigot connections between each bone. We've done a few artworks with sort of concealed spigots before. That would have been incredibly difficult and wouldn't have been strong enough. Without that upper tendon, the neck and tail have a real tendency to sag quite a lot. So the pre-stress of that upper tendon was really important. It was first proposed, I think, by my director, Pete, as a really, really early sketch, just as an idea. And I don't think it was taken seriously for a while because it was quite out there. But by considering every option, we slowly came to realize that it was the only viable approach to do it without props, essentially, and to make it makeable and safe.
Yeah, excellent answer. Then we have a few technical ones, not surprising ones. Someone asks about the risk of bimetallic corrosion
Yeah.
between the macroloi bars, stainless steel, and the bronze.
Yep.
Uh, was there a
Yeah.
risk? How do you mitigate it?
Yeah, I can see that one. Yeah. Yeah, I've got them up here as well, so I can see which one you're referring to. Yeah, though that is a risk. Fortunately, they're not too far from each other in the galvanic series, but yeah, whenever you have dissimilar metals, you have to be cautious of bimetallic corrosion, particularly as this is outside, so it's going to get wet, and it has a long design life. It's a monumental thing. They want it to be there for over 100 years. And so the way we dealt with that was by isolating the two metals. So that those tendons that you can see are actually all coated in black PTFE, also known as Teflon. So often you can get bolts that are coated in that, and so we had to find, with Macklo's help, a sort of an oven big enough to take these long tendons and coat the whole things in PTFE. So that isolates the metals, and it also means those tendons are sort of they're black instead of shiny silver, and you can see them, but it sort of retreats them to the background, which I think is appropriate because the focus should be on the biology of the thing and not the engineering, which is always our focus. So that's how we dealt with that one.
Here,
Yeah.
just well, link to that actually. How do you decide the lifespan of a sculpture like this? Is close to what it will be in a bridge? Is something that the client asked for, or you thought it
Yeah,
would be a
well,
risk?
yeah, it is something the client asked for. So they're obviously a institution. Dippy itself has been around for 120 years, and they want to have a asset that will, you know, be appropriate to the kind of institution they are, which is, they're going to be around in 100 years. They want this thing to be. They don't want it to have to be taken, you know, thrown away after 20 or even
Yeah.
50. So yeah, it's definitely a question for them, and that really set the challenge for us to try and meet it. And the great thing about the bronze is, they dig up bronze swords and stuff from like hundreds and hundreds of years ago.
Should last.
So it's quite a good material for it.
Did you? Sorry, I'm squeezing my questions as the topic gets close to them. Was inspection and maintenance manual part of the work you gave the client?
Uh, there is one. We fed into it, but Factum are the real like sort of experts on bronze and maintenance of bronze. And on that topic, yeah, originally in terms of maintenance, it was supposed to have a patina, and they were going to apply a patina to it, so it would have gone very dark brown very quickly. I'm not sure exactly the process, but I think once everyone saw it in its pure shiny bronze, I think there was a wide agreement that they could leave it as is, and it's going to patinate naturally, slowly over time. But yeah, when it first got installed, it was an amazing shiny bronze thing.
It adds to the story, not that it works naturally with time. The next question is about how you touched that, I think, a bit better, how you build the trust with the client so they could know that you could do it and invest in the project.
Um, I suppose trust was built up at two key stages, one at competition just to win the project, and then one while we were busy proposing some unprecedented structures. How would they go along with it? We have a lot of experience doing sculptures and unusual structures like that in public settings and in bronze, and indeed so do Factum. So at that first stage, it was sort of, you know, trying to demonstrate our breadth of experience and that we've done things like this before. At competition stage, it wasn't known what exact structural approach we'd take. We had some sort of ideas. So I think at that stage it was sufficient to show we had experience in similar structures. And then during the actual design, how do we demonstrate that the uh, unusual thing we were proposing would work? And I suppose there was an element of trust from the museum. You know, they had the ambition to propose this thing. They wanted to see it work. And we demonstrated at a few key meetings what our proposals were. But, you know, they were hiring us. We were the engineers and the designers. We were the experts. So it was sort of us telling them it would work and them. I guess we were convincing. That's all I can say through our
Yeah,
presentations. But yeah, first we had to convince ourselves, which took quite a lot of work itself. So we had stuff to show them, I guess.
yeah. Well, I guess sometimes it's a but it's about attitude. No, if they see you trying with the skills and trying to learn, that builds confidence as well. Very good. There was a question about the name. Do you know why the specimen is called Fern?
Yes, roughly I do know. Yeah, it was sort of internally called Dippy for a long time because it didn't have a name yet. But it's very important that it's not Dippy. It is a separate thing to Dippy. It was named by school children, I think, local school children. There was a competition to name it. So I don't know who was the winner, but yeah, school children chose the name Fern, and I think there was a shortlist, and yeah, it didn't end up being Dino Face or anything like that. I think Fern's quite a lovely name.
This is a very good name. Yeah, it feels that was born to be named Fern. There is a question about another technical question about bronze behavior in fatigue. How does it work given the large movements that could happen?
Mhm. So bronze is quite good in fatigue, but any casting will typically be, you know, it is a danger. Um, yeah, that question notes movement, and what's quite interesting is it moves a lot, but the stress variation due to that movement is very small. So all the biggest stresses are gravity, and they're completely static. The stresses due to wind loads, the vibrations cause very, very small stress ranges. So that really reduces the risk of fatigue. And again, additionally, because of the pre-stress nature of it, a lot of the major stresses are in compression, which again is less of a problem than when they're in tension. So because of those two aspects, we managed to sort of demonstrate that fatigue wouldn't be a problem even over the long lifespan of this thing. Because if you ever go on a windy day, that tail does, you can see it moving around a little bit, back and forth, back and forth.
Yeah, so we'll need to go there on a windy day to see that. Right?
I have done.
Yeah.
When the storms came this January, I was down there to
It was the
check it
first
out.
time you okay.
Yeah.
A long life obligation has been created for you. There's a question about the type of finite elements you used in your models, if they were
Mhm.
shell or continuum or solid.
Yeah, so I flashed up a few little images of them. It was definitely the most challenging thing I have ever had to model, to sort of fully capture the design. And yeah, we basically decided it was easier to just do the whole thing than to try and find a simpler approach because it was so complicated. Every little thing was so different. So the answer to that question is most of it is a plate model, you know, made out of 2D plate elements. Um, but because the bones they curve quite a lot, they have quite delicate structure. We weren't sure how you know with how accurate this plate model would be. So certain select bones were modeled using 3D brick elements, which actually where a plate model is 2D and you apply a thickness to it. With the 3D elements, we modeled the thickness of each bone, and that's what I showed you in the modeling process earlier. And we use them to sort of verify the accuracy of the plate model and to make sure um, that reality was actually, yeah, what we actually found was the brick model, the stresses come out lower than the plate model shows. So we felt that was a good approach and we felt it was accurate enough. I don't think we could have got it to run on our machines if the whole thing was done in 3D elements.
It's surprising that you managed, even with the 2D elements. Yeah. Another question is about the post-tension age. I think you partly explained that before with another answer. If the post-tension strands are in a sheet and crowded.
It's a good question. Yeah, because that's how it's often done, particularly with more conventional post-tensioning materials like concrete or even stone these days. That wasn't our approach. So our tendons are sort of loose, as it were, with inside the bones, and they contact the bones at every cartilage plate. So between every bone, they come into contact, and then they are actually locked off. So the tension is applied sort of every 3 or 4 bones. No, so there's no sheath, no grout.
Then another question is asking if you would expect for this to be the first of many, if this will set a
Now, I don't know
precedent.
if I expect it, but I would love it to be. When I got into this project, I thought it would be great to design a dinosaur. Probably the only one I ever get to do. Um, if I got the opportunity to do more, I'd certainly would. And if there's any museum curators watching, give me a call, please.
Surprisingly, then yeah, that was an interesting one about the weight of the finished project compared to the real DP, not the DP the cast, but DP the dinosaur itself with skin, bones, guts. I know.
Yeah, well, I don't know if this is counterintuitive or not, but the bronze dinosaur is much lighter than the real dinosaur. Our bronze dinosaur is somewhere between 5 and 6 tons. And I think a real Diplodocus would have been in the region of about 20 tons. So yeah, about 4 times as heavy. Because a bronze, it's only a skeleton, and then all those bones are hollow. So when you feel one of these bones, it's really heavy. But then yeah, nothing compared to the real beast.
And another one is related to maintenance again. So, what does the maintenance entail? Probably high
Yeah, so
level.
yeah, high level. I mean, like I said, Factum have developed the maintenance schedule. How it will age is in some respects not fully known. We expect it to basically be able to stand up there for 100 years. The advantage of the way we've designed it is that if you wanted to, you could take it apart down to every single bone and then reassemble it again. So if you ever did need to clean it or maintain it. So the answer is I'm not fully across the exact maintenance schedule. I think the answer is it's minimal, but they will probably check it probably after the first year, then probably after 5 years to see how it's aging. But most of the materials have been selected for their longevity.
And then there is a question that overlaps with another one about the project, how long the project did take from designing, manufacturing, installation to being open to the public. And someone else is asking about how long the design process takes. So
I
you can
feel like it
answer.
took up about 2 years of my life. It was there were pauses in that for approvals and then a pause between design and construction. I would say we probably were working solidly on it for only about 9 months, and I wish we'd had a bit longer because it was quite a pressured thing. 9 months spread over about a year and a half, I would say, and then took them about a year, just over a year to make it, which was fast considering how much they had to do, I think.
Yeah, feels fast, yeah, compared to other
Well,
structures we
exactly,
design.
yeah,
Yeah,
exactly.
yeah, very good. And there is always a question about cost. Although is ask Chris, and origin is rude to ask, but how much did this cost? Do you know? Is it you can you tell if you know it?
I'm not privy to
You
that information, I don't think. All I would say is if we did it again, we'd probably charge more for it than we did. But what I would say is I do think it's good value, how much it cost. It's you know, I'm trying to think. I don't actually know the answer. I'm not even sure if I'd be allowed to say if I did know
I wouldn't expect so, but I think it's yeah. I would agree with you that that's this is the kind of excellent value interventions that will make people happy for a long time. So yeah. I think that's this. We have a 16. We'll have one more. Another technical one about creep. If it will affect too much or more over time, and if there is any way to rectify it if it does.
Yeah, so will it move over time? The answer is it will move over time. Creep, we don't think is going to be a big issue for a couple of reasons. One, the tendons themselves, like I said earlier, are solid bars rather than strands or ropes, and they do tend to stretch and creep a lot less than metal cables, for example. And the other thing to note is in its sort of typical state, under just its self-weight, the stresses in those tendons are sort of well below their capacity. It's only in like the most extreme load cases where there's lots of people hanging off the neck and tail that they start to reach high levels. So we're not hugely worried about creep in the long term. I think it might be minimal. It does move over time due to temperature variations as well. That the bronze and the steel expand at different rates when the thing gets warm or cools down. So we actually think the head probably rises a little bit over the year and sags a little bit too. We think that's probably going to have slightly more impact than the creep, which is quite interesting, I think. But I don't think you'll really notice that either.
New one. This about fabrication. If there were unexpected delays in the fabrication and construction, and if there were, how they were tackled.
There were many unexpected moments in fabrication because we were like asking quite a lot of them, Factum, and there was a lot of problems to challenge on the way. So when we put down our pens and finished the design, yeah, that was not the end of the process for us. You know, every bone was different, so it was very hard to get that casting process just right because you didn't have sort of a big run of bones to practice on, and so the bones would sometimes come out too heavy because we had a weight limit on them to make sure the thing worked. Sometimes with the walls too thin. The extent of distortion in those bearing faces, which had to be perfectly flat, I don't think was fully appreciated by all of us right at the outset, and that was a problem that had to be solved. And the approach to CNC milling it, although we thought we'd have to machine them in some way, the CNC milling approach was something we had to figure out, sort of fact and figured out sort of on the fly, as it were. Yeah, so these bones distorted a little bit more than we expected, and we had to sort of figure out how to account for the tolerance in putting it together and having the bones fit with the tendons. There was a little bit of shimming going on, and yeah, that CNC thing was a really clever move, I think.
So I think that's the last of the questions that we have listed. I have a couple of small ones. Have you, or was the tail needed to be replaced already, or is it still in
No, and I'm
place?
hoping it never will be, to be honest. It's sort of out of reach, really, and we wouldn't expect it to break in any normal load case. It would take a committed idiot to break that tail. So yeah, hopefully not.
And another one. I hope you don't find that one depressing, but do you feel this will be the most exceptional project in your career?
Well, you're not
And
the first person to ask me that. So
what are you going to do about it?
I
Given that
think,
you still have quite a bit of career to go.
yeah, have I peaked? You're asking me. I think as a child who was obsessed with dinosaurs, I don't think, yeah, there'll ever be a project I would imagine that means quite so much to me. Um, I took my niece there the other day and she calls it, there's a lot of people involved in the project. She calls it Uncle Max's dinosaurs. So, it makes it all worthwhile. And I'm happy if this is the most interesting thing I ever work on because it was brilliant.
Actually, now you said that, I believe I skipped one question that was asking about how many people work in the project. Yeah. Do you know how many people work in the project? Or at least, well, maybe you can split your
If I had
side
to
on
name
that.
everyone involved in it, I couldn't because on the fabricator side, like I said, there was probably dozens. The core design team at Structure Workshop was just, my director and I, because you had to really, really get your head into it. it was not a project that we could really like delegate much. So sort of, yeah, there was us at Structure Workshop, and then a few key people at Factum, and then, as I said, dozens of like really skilled craftspeople and technicians.
Yeah, the kind of detail you show requires immersion in a project for a long time, no? Of committed and skilled people. So I think that's it. Has been a fantastic presentation. Really enjoyable, really exciting, very well done. Thank you for that. I think the proof of that is that most of the people who joined are still here, although we are a bit overrunning. So yeah, thank you very much to everyone who have joined, and yeah, thank you very much, Max. That was excellent.
Thank you.
Thank you.